cosmology. Ultimately, it would validate our story of the origin of the very first atoms. As with many of us, Dickey found the idea of the Big Bang a little conceptually troubling. How can something come from nothing is perhaps the most asked question about the universe's origin. So Dickey explores the idea of cyclical universes, an expanding universe that slows, stops, and shrinks, collapsing back in on itself in a big crunch, only to explode outwards again in another Big Bang. A collapsing universe would get exceptionally hot as matter crushed down on itself. Electrons would get ripped away from protons as the universe returned to a sea of subatomic shrapnel. Dickey dubs this mega-hot maelstrom a fireball. The ensuing bounce and expansion would cool the fireball back down and allow atoms to reform, and this is where the name recombination originates. In this theory, the atoms truly would recombine. By thinking this scenario through, Dickey, like Gamow over a decade earlier, hits upon the notion that there should be some relic radiation left over from this superhot stage, and that it would still be visible today. He calls it fireball radiation, and it's the same radiation from recombination that Gamow and his colleagues predicted back in 1948, although Dickey is initially unaware of their work. Dickey reasons that this fireball radiation should now be in the microwave part of the electromagnetic spectrum, the very part he has spent 2 decades working on. Of course, initially, the leftover light from the Big Bang would have been in the visible part of the spectrum. Had anyone been around to see it, it would have glowed yellow-orange. But the universe has continued to expand ever since the light was released 13.8 billion years ago. That expansion has stretched the space between everything, also redshifting any waves of electromagnetic radiation traveling through that space. Dickey calculates that this fireball radiation would have been stretched right out through the infrared and into the microwave spectrum, and so he resolves to find it with his eponymous radiometer and begins to plan an observation run that would start in the mid-1960s. But something strange happens before he has a chance to finish his work. 45 minutes drive away in Homedale, New Jersey, 2 radio astronomers are attempting a different kind of experiment. Their names are Arno Penzias and Robert Wilson. Like Gamow before him, Penzias fled European totalitarianism, a child evacuee from Nazi Germany. Penzias and Wilson are using the giant 6-meter Homedale horn antenna, part of Bell Telephone Laboratories, to listen out for radio waves reflected off orbiting satellites. The signals they are looking for are very faint. To hear them, they must first get rid of any other interference. They eliminate local radar and radio transmission and even remove interference from the receiver itself by cooling it to -269 degrees Celsius using liquid helium. Yet despite their best efforts, there remains an annoying hiss in the detector, like the static between channels on an old radio. Where could it be coming from? It seems to be coming from all over the sky. And it is then they spot what must be the culprit. Penzias and Wilson discover pigeons roosting in the antenna. The heat from their droppings, what they would later call a white dielectric material, must be creating the noise. The pigeons are carefully trapped and sent to the town of Whippany, 30 miles away, only for them to fly right back. In the end, they sadly meet their demise. Penzias and Wilson meticulously clean out their droppings, but the hissing remains. In all, Penzias and Wilson spend over a year trying to figure out the source of this maddening interference. Desperate, Penzias starts phoning round, asking others if they have any idea what's going on. Dickey is in his office, in the middle of a meeting about building his device to look for fireball radiation. As soon as he hears what Penzias has to say, his heart sinks, and he says to his colleagues, "Well, boys, we've been scooped." Penzias and Wilson pick up the 1978 Nobel Prize in Physics for their serendipity, and Dickey is left empty-handed. Gamow would never win a Nobel either. And so ends the story of the discovery of the cosmic microwave background, the unmistakable fingerprint of the formation of the first atoms, undeniable proof that our universe started with a hot Big Bang. As the earliest light dispatched into the universe, it is an image of an infant cosmos. If our present universe were a 40-year-old human, the cosmic microwave background is the equivalent of a photograph taken when it was less than 10 hours old. Hidden within it are clues to the universe's future, our present. Small temperature variations signal the existence of tiny differences in density in the infant universe. The more matter that falls into these densities, the bigger they get, and in turn, the more matter that falls in. Within a few 100 million years, the first galaxies will form as matter relentlessly clumps together. And along with this, marked across this map of the cosmos, now stretched to almost 500 million light-years in diameter, are the imprints of the sound waves of the early universe, the remains of the baryon acoustic oscillations. Experiments such as the Dark Energy Survey high up in the Chilean Andes have mapped the layout of the modern universe like never before. Vast superclusters of galaxies stretch out among equally gigantic supervoids, which mirror the tiny temperature variations seen in the cosmic microwave background. The seeds of the universe's structure were sown long ago. But you don't need a giant horn antenna to tune into the universe's youth. In fact, an old analog television set will suffice. In our modern digital age, memories are fading of the snow that would settle across the screen as you twiddled between channels. 1% of that static is the cosmic microwave background. The universe began almost 14 billion years ago. But the formation of the first atom was such a monumental moment in its history that echoes of the event remain our invisible companions throughout our lives and will take trillions of years of expansion yet to be stretched out beyond our view. And so, you may be forgiven for thinking that the rise of the atom was inevitable, the final destination of any hot, dense soup of particles, as fundamental to reality as their constituent parts. But that is certainly not the case. In fact, it is quite the opposite. With the blindfold covering your eyes, your other senses are heightened. You hear every click and snap as the guns are loaded, all 24 of them. You are about to be executed by firing squad. The soldiers raise their weapons and aim the barrels squarely at your chest. This is it, you think, and your body braces for its last breath. Then, every single bullet misses. The Canadian philosopher and author John Leslie asks us to imagine a version of this scenario in his 1989 book, Universes. How unlikely it seems that you're still alive. It only needed one shot to hit its target, and yet every single gunman missed. You owe your existence to an incredibly precise and improbable sequence of events. Any deviation from it, and you simply wouldn't be here. The story of our universe and of its atoms is a similar tale. Since its birth 13.8 billion years ago, the universe has gone from having no atoms at all to being full of more atoms than we could possibly count in trillions of lifetimes. The atom is so ubiquitous that we take it for granted. Atoms, after all, are everywhere. And yet the atom is a ludicrously unlikely entity. Like your life in that courtyard, it teeters on a tightrope so fine that any minuscule misstep would see it snuffed out in an instant. Mess with the physics even slightly, and every trace of chemistry and biology would fade away. Imagine that you could operate the universe using a giant control panel, littered with knobs, dials, and switches, each one responsible for some key property of existence, the masses of certain subatomic particles, the strength of the various forces. In this scenario, it wouldn't take much tinkering to destroy atoms entirely. For an atom to be stable, the orbits of its electrons need to be a lot bigger than the size of the nucleus. Otherwise, the electrons risk crashing down on the atomonaut's homeworld of the proton, like a satellite dragged back to Earth in fire and fury. You'd only have to make the electromagnetic force a little bit stronger, and electrons would be pulled in tighter. Weaken it, and electrons could fly off on their own, like stars flung out from a distant galaxy, rendering them forever out of our atomonaut's reach. Or you could weaken the strong nuclear force. Then protons and neutrons wouldn't hug each other so tightly, increasing the size of the nucleus and hastening the electron's demise. A physicist would say that these forces appear finely tuned. The dials have to be in pretty exact locations, otherwise atoms wouldn't exist. And one of the first people to discuss this so-called fine-tuning in detail? None other than Robert Dicke, back in 1961. Electron orbits are far from the only aspect of the atom that appear finely tuned. The neutron, for example, is a mere whisker heavier than the proton by about 1/7 of 1%. Physicists know this thanks to increasingly precise experiments. Indeed, in 2021, a pair of researchers from Florida State University measured the deuteron to proton mass ratio to an accuracy of 4.5 parts in a trillion. This small difference in mass between the proton and the neutron is greater than the mass of the electron. And this is key. Were the electron heavier than the difference in mass between its two bulkier cousins, it could be captured by a proton and turned into a neutron. In other words, you can't change the masses of electrons, protons, or neutrons by much either, or again, atoms simply wouldn't exist. Fiddle with the control panel further and you can cause more mayhem. The reason the neutron is heavier than the proton is due to differences in the masses of their quarks. As we saw earlier, a proton is made of 2 up quarks and 1 down quark. 2 downs and 1 up form a neutron. The down quark is ever so slightly more massive than the up quark, so a neutron is heavier than a proton. Yet these masses appear finely tuned as well. If the difference in mass between up and down quark were larger, the entire history of the universe would have been radically different. A down quark would be able to decay into an up quark. If that happened inside a neutron, suddenly the neutron would become a proton. The deuteron, the key marriage of a proton to a neutron, would be annulled. This means no fusion after the Big Bang and a universe that only contains atoms of hydrogen. None of the 117 other types of atom or elements in the periodic table would exist. No oxygen for you to breathe or iron to carry that oxygen around your body. Changing the mass of the quarks isn't the only way to snuff out the deuterons. They only exist because the strong nuclear force can bind a proton to a neutron in the first place. Make that force just 9% weaker and it would be too puny to hold deuterons together. Going the other way, ratcheting up the strong force by just 2% would have even more profound consequences. It would then be strong enough to bind 2 protons together, a form of hydrogen called a diproton. We've never seen one in the real universe, and there have only been tantalizing and unconfirmed reports of one inside experiments, such as the radioactive isotope beam factory in Japan. Had they existed after the Big Bang, they would have rapidly fused into helium, and all hydrogen would have quickly disappeared from the universe. We live in a helium-dominated universe instead of a hydrogen-dominated one. And so, whichever dial, switch, or knob we contemplate on the great control panel of the universe, it is surprisingly easy to eradicate atoms. In other words, all the settings appear to be in exactly the right place to permit atoms, and the things that they are built from. It seems quite the coincidence. It is as baffling to physicists as your survival in front of the firing squad. And so scientists and philosophers have put forward 3 broad ideas to explain the fine-tuning problem. First of all, maybe it's just dumb luck. After all, the settings all have to be somewhere and, although almost impossible, they could have fallen in the right place so as to give rise to the first atom some 380,000 years after the Big Bang. By one account, the odds of this are about 1 in 65 billion trillion. That's roughly the same odds as you selecting the sun when asked to choose randomly from a bag containing all the stars in the observable universe. Many find these odds too extreme to accept and see this apparent fine-tuning as evidence of something or someone with a steady hand on the tiller. In other words, not being an accident, but the deliberate act of manually setting the dials to the right place. This could be some omnipotent deity or a bored advanced civilization who wants to create their own real-life version of The Sims. There is another option, though. Thanks to strands of evidence like the cosmic microwave background, cosmologists are confident that the universe began with something like a Big Bang. But what banged exactly? When trying to answer that question, a tantalizing possibility emerges. The Big Bang is a good theory, but not a perfect one, and some scientists believe the cracks can be papered over and the theory salvaged if there was more than one bang. Perhaps an infinity of bangs, each one giving rise to a new universe. The settings on the control panel of each universe could therefore vary depending on the exact way the universe emerged from the cacophony, and all possible settings would be found across this endlessly large multiverse. So which of these universes are you going to find yourself in? You can't be in ones in which the dials are set so as not to permit atoms, and in turn the stars and planets made from them. You, a giant lump of atoms, can only find yourself in a universe where the strengths of the fundamental forces and the masses of the subatomic particles allow atoms to form. And what a journey those unlikely atoms have been on. Their constituent parts forming within minutes of the Big Bang to coalesce at recombination before hurtling across space, spinning into stars, exploding back into space, pulled into planets, and eventually ending up inside a brain capable of contemplating its place in this vast and intricate universe. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time. Wolfgang Pauli was one of the most brilliant physicists of his time, but he was also savage in his criticism. Happy to use his considerable wit to tear apart ideas or theories he thought lacking, he took to signing off his letters with the title Die Geißel Gottes, German for the Scourge of God. But perhaps most famously, he once solemnly responded to a young physicist's earnest paper with a simple but brutal epithet, that the offending work was not even wrong. Although not all ideas have a Pauli to puncture them, most scientific theories do end up dead and forgotten. Most scientific theories fail. They may have had their day, they may have been widely believed the focus of papers, seminars and conferences, only to end up a footnote in the history books. Once upon a time, it was thought that something called phlogiston existed. Residing inside objects, it was released when they were burned. During the 18th century, the theory of phlogiston was one of the foremost explanations for heat and combustion. Professors taught it, students learnt it, and the chemists of the day attempted to interpret their results with it. But the idea, very simply, was wrong. The phlogiston account of heat was a fantasy. The truth, as we now know, lay in chemistry and the combination of different elements in various chemical reactions. Somewhere, at some point in history, the last believer in the phlogiston theory of heat died. In the mid-20th century, there were two competing ideas for understanding the origin of matter in the universe. One was the Big Bang theory, the idea that the cosmos was once extremely small, dense and hot, and then expanded into the vast cosmic structures we observe today. But there was also another competing theory, the so-called steady-state theory, in which matter was constantly being created to sustain the universe so that it remained on large scales eternally the same. At one time, the steady-state theory was one of the most discussed ideas in astrophysics and cosmology. Even Einstein had an interest in it. But over the years, evidence piled up in favor of the Big Bang, and with the discovery of hugely powerful quasars at cosmological distances, which dated from the younger universe and have no counterparts today, gradually the lights went out for steady state. The last conference was held, the last talks were given, and the last adherents of the idea retired, leaving only filing cabinets packed with old, yellowing notes. And so we arrive to the present day, and the ongoing quest for a fundamental theory that explains everything within our universe. The quest to unite the two pillars of general relativity and quantum mechanics. Our current leading frameworks for quantum gravity are known as string theory and M theory. Ideas which claim extra dimensions and tiny vibrating strings exist deep within everything at the as yet unobserved heart of nature, or even vast multidimensional brains stretched across an imperceivable bulk. Many physicists and mathematicians are working on these cutting-edge ideas. Regular conferences are being held packed with both young and old, all chasing the holy grail of physics, a unified theory that explains it all. But will these theories last? Do they really represent viable solutions to the fundamental questions of the universe, or a tragically misled community lost in elegant mathematics with no hope of finding connections to the real world, let alone a shred of testable evidence? Will, one day, string and M theory too be found as dusty footnotes in fading tomes? Are they, as Pauli once mused, not even wrong? This year's Nobel Prize in Physics was awarded for research into quantum entanglement, leading to deep questions about whether our universe is even locally real. Unfortunately for controlling our devices, our macroscopic world does appear to have different locations. This is where our sponsor, AnyDesk, comes in, the best remote desktop software on the market, helping you access any device, anywhere, anytime. From IT support to easily working at home, from super straightforward file transfer to controlling everything with just your mobile, AnyDesk is a secure and fast way to stay on top of things wherever you are on Earth. But not if you are light years away. It is also easily customizable and smoothly runs on all major operating systems. And most importantly, it's very simple and straightforward to use. So try it out for yourself at anydesk.com. They have a great free version for non-business users. Thanks to AnyDesk for supporting educational content on YouTube. What is meant by fundamental? Push distances inwards. Start with us, bipedal members of Homo sapiens sapiens, normally standing a bit over 1.5 meters. Focus our view narrower and narrower, first to the scale of insects, little creepy crawly objects 1 centimeter across, a factor of 100. Next, head down to the size of cells, the powerhouses of human metabolism. That brings us down by another factor of 10,000, reaching micrometers. We go again. Another scaling down by a factor of 1,000 brings us first to molecules and then to atoms and the quantum mechanical bonds of electrons in orbitals that hold atoms together to form the building blocks of life. We are now at distances slightly less than 1/1000th of a meter, where quantum mechanics rules. If we were to look around in a little cube 1/1000th of a meter across, then the number of such cubes that would fit inside our body is greater than the number of stars in the observable universe. And yet this is only the start of our inwards journey. At the center of atoms lies the nucleus, the radius of the nucleus 100,000 times smaller than the size of the atom itself. The nuclear ball consists of protons and neutrons, little clumps of quarks both held together by the strong nuclear force and also attracted to each other by the strong nuclear force. We are now at distances of 1 femtometer, 1/1,000,000,000th of a meter, and entering the realm of particle physics. Particle colliders are our world's most powerful microscopes. Using these, and in particular the Large Hadron Collider, we are able to probe inwards by an extra factor of 1,000 to picometers. But no more. The realm beyond this is the realm of theory, where we would continue to go inner, deeper and further until we reach the scales on which our ordinary classical notions of space and time break down, and must be replaced by some quantum mechanical replacement for the classical theory of space-time described by Einstein's theory of relativity. Calculations suggest that this would occur at a distance of 1 million-billionth of a picometer, where quantum gravity will take over. And it is at this distance scale we perhaps reach the scale of strings. Relativistic quantum mechanical strings that some physicists say may be the most fundamental building blocks of the universe, what everything is truly made of. And yet, surprisingly, this idea, string theory, did not start off as a potential fundamental theory of nature. To climb back up the ladder, at distance scales of around a femtometer, only 1 million-billionth of a meter, we are in the realm of the strong force. The strong force, which, at one point, many people believed was actually a string force. String theory started its life in the summer of 1968 as a possible theory of the strong nuclear force, a candidate to explain the forces in interactions that hold protons and neutrons together. The first paper on string theory arrived in Berkeley in the summer of 1968. Everyone had stopped what they were doing and were asking if this idea could be extended. However, it did not turn out to be a success. In this string theory account of the strong force, the internal structure of protons and neutrons involved strings, not particles. This made a clear prediction. When launched towards each other at high energies, these particles would slop off each other like balls of jelly and not bounce like hard billiard balls. And so in the early 1970s, these experiments were carried out, and careful measurements revealed that the number of these hard scattering events was far in excess of what was predicted by the string theory of the strong nuclear force. As a theory of the strong nuclear force, string theory died in 1973, to be replaced by the correct theory of quantum chromodynamics. But in theoretical physics, sometimes death is only the prelude to resurrection. Some felt that there was something too neat about the calculations in string theory, beautiful features that had no obvious reason to be present, and yet were. And so, throughout the 1970s, some physicists, notably John Schwartz of Caltech and Michael Green of Queen Mary in London, continued to develop string theory, not as a quantum theory of the strong nuclear force, but as a potential quantum theory of gravity itself. Many times it seemed that the theory was on the verge of failing, of being ruled out as simply inconsistent with the laws of quantum mechanics. It only seemed to work where there were precisely 9 dimensions of space, neither more nor less. But then always there was a way through that made the theory appear ever more unique. During the 1980s, string theory became established as the leading candidate for a quantum theory that would include gravity. A theory where you could put both gravity and forces like electromagnetism together in harmony for the first time. Perhaps some dared to dream in proud and foolish dreams. All aspects of particle physics would be uniquely singled out. Everything could be predicted with strings. However, by the late 1980s, one aspect of string theory appeared odd. It had been touted as the theory, at least in universes with 10 flat spacetime dimensions, the singular answer to all of the problems of particle physics. The only problem was that there was not just one string theory which existed in 10 dimensions. There were 5 of them. The type 2a string theory, the type 2b theory, 2 type 1 theories, and finally something called the heterotic string theory. The theories all had slight differences. Both the type 2 theories and also the heterotic theory were what is called closed string theories. All the strings involved were closed loops reaching back on themselves like elastic bands. They had no ends. Between themselves, the internal dynamics of these 3 theories also differed slightly. The strings in each case behaved in different ways. The type 1 theories also included closed strings, but in addition, open strings. These were not closed, but instead had endpoints vibrating at the speed of light like a perpetually cracking whip. The open and closed strings differed in their interactions. While the closed strings behaved more like gravity, the open strings behaved like generalization of the electromagnetic, weak and strong forces. And so, 5. 5 is not a large number, however, it posed a puzzle. 5 is not 1. To any ambitious, possibly arrogant physicist hoping that string theory might be the unique theory, even 2 would have been one too large. Given the existence of 5 consistent theories, what singled out one of these 5 theories, as opposed to any of the others, as the chosen one? The presence of 5 different theories did not imply that each theory only had one solution. In the same way that our ordinary theory of gravity contains as a solution both a single lonely rock flying through space and the full complexities of our solar system with satellites orbiting moons, orbiting planets, orbiting the sun, so each of these 5 string theories admitted many different possible solutions for their equations. There may have only been 5 possible sets of fundamental equations, but the number of solutions was effectively unbounded. But still, in terms of the fundamental equations, there appeared to be 5 choices. And 5 is not the same as 1. In an ancient Indian parable, an elephant wanders into a town where a group of blind men are sitting. The blind men can hear the beast and decide that they need to touch it to get a sense of what it is. One places his hand on the trunk, reaches around and feels along it. "I know," he announces. "The being is a type of snake." Another man touches one of the elephant's legs and feels how large and strong they are. "No," he says, "this is a kind of walking tree trunk." A third man finds his hand on the tusk, hard, long and sharp. "You are both wrong," he says. "This is a moving war machine." Each could feel one part of the animal, but none of them could see the coherent mega-animal that is the elephant. Viewed from today, the physicists of the 1980s studying 5 string theories are like the blind townsfolk touching the elephant. And that is because today we think of each of these 5 theories as different limits, different boundaries of a single underlying object, one both deeper and more mysterious. Not an elephant, but M theory. And whether M stands for mystery, magic, or something else has been left open to interpretation. Of course, the idea that 5 similar but different string theories were actually aspects of one single whole would have appeared bizarre and surprising. That is, until Edward Witten spoke at the 1995 Strings Conference. Edward Witten is the physicist who almost never was. Widely regarded as the premier mathematical physicist of his generation, his undergraduate degree was in history. After briefly assisting on the 1968 McGovern presidential campaign, he decided that his principal interest lay in the sciences. Still unsure that he would be able to catch up, he initially applied to do graduate studies in economics. Fortunately, Princeton saw through his background to detect the innate talent and took him on as a graduate student in theoretical physics. Theoretical physics and pure mathematics are 2 subjects divided by a common language. Although both use similar notation, their ways of thinking and standards of rigor are very different. To a mathematician, physicists are frustratingly sloppy, with a fundamental inability to give precise definitions. To physicists, mathematicians are so obsessed with rigor and proving results that are obvious, they can never address problems that actually matter. Witten's great gift was that he was fluent in both languages, and rose to prominence at a time when the interface between physics and mathematics had been long neglected. He reignited the relationship, using quantum field theory and string theory to draw many deep connections between the 2 subjects, resulting in him becoming the first physicist to win the Fields Medal, the premier prize in mathematics. And so, by 1995, a long list of discoveries had turned Witten into the person everybody wanted to hear. As participants finished their welcome coffee and settled down for the 9 a.m. talk on the 14th of March at the 1995 Strings Conference, some of them had an inkling that they were about to witness something special. But as Witten got up and began talking, the audience soon realized that this was something truly monumental. For he was describing a wholly new map of string theory. There were not, Witten claimed, actually 5 fundamental theories, but really only one, and the 5 string theories and one extra non-string theory called supergravity should be viewed as being on the boundary of one even more fundamental, M theory. This one theory was continuously connected through a mysterious interior, in the same way that flourishing coastal cities like Perth, Darwin, Adelaide and Sydney are all part of the single continent of Australia, filled with a large interior desert. The path through the interior may be difficult and complicated, but it does exist and joins these boundary cities together. Indeed, the M in M theory didn't stand for anything in particular, but had been chosen as a placeholder of sorts, the word beginning with M to be finally decided in the future, when more about the theory revealed itself. And what was more, said Witten, M theory was 11-dimensional, not 10, and the fundamental objects of this 11-dimensional theory were no longer strings, but a mysterious object taken from supergravity, the 6th theory. The fundamental objects of M theory were brains. These were extended objects stretching through more than one spatial dimension. When some of these spatial dimensions became very small, the brains could wrap around them and look like strings, and in these situations, the 11-dimensional theory could, in practice, be described as a string theory. So, for 10 years, string theorists had been working obsessively on a theory of strings, on string theory as the proposed fundamental picture of nature. And now, the most dominant intellectual figure in the subject was saying that it was not strings, but rather higher dimensional objects called brains, which really mattered. But what were these mysterious brains? And how can we visualize them? Start with a string, a one-dimensional object under tension, a violin string or wire, a long thread. At heart, the strings of string theory are just one-dimensional extended objects, and all the physics from string theory flows from studying the relativistic quantum mechanical theories of one-dimensional extended objects, moving and oscillating their quantum mechanical relativistic way through space. A brain is basically a version of this with more dimensions. The name comes from membrane, the two-dimensional version, a taut surface. Think the skin of a drum, the boundary of a cell, or the surface of a soap bubble. A two-brain is an object extended through 2 spatial dimensions, a 3-brain extended through 3 spatial dimensions, and so on. A 1-brain is simply a string. While it is relatively easy for us to visualize stretched objects with 1 spatial dimension, or 2 spatial dimensions, mathematics happily extends this idea to even more spatial dimensions. For example, the equations can define, even if we cannot visualize, an object with 4 spatial dimensions extended within a space of 9 spatial dimensions. And so, the world of M theory, Witten told his audience, was one of 11 dimensions, and with brains, not strings, as the fundamental objects. Different lower energy limits of this 11-dimensional world, in which one of the dimensions became small, produced the 5 10-dimensional string theories the audience were already familiar with, the string theories that could be the quantum gravity theories of our world. In these lower energy situations, like our universe, the brains of M theory, in particular something called the M2 brain, turn into the strings of 10-dimensional string theories. But what does this all mean? How can a brain turn into a string as one dimension becomes small? What, indeed, does it even mean for a dimension to become small? There is no way to make this perfectly intuitive, but we can meet our intuition part of the way. How might extra dimensions be real, but yet unobservable? One way to have a sense of this is to imagine an insect walking on a plant vine. a vine both long and thin. An ant or any other insect can walk along the vine either forwards or backwards. The surface of the vine certainly has 2 dimensions. Zooming in with a powerful microscope, we would see the surface made up of many cells, stretching off in all directions. But the insect, small though it is still too large to treat the vine as having anything more than 1 linear dimension. In truth, the surface of the vine has 2 dimensions, but to a big enough insect, there is effectively only a single dimension. As for the ant, so too, perhaps, for us. If these extra dimensions are small enough, we and all our technology are simply too big and too clunky to resolve them. Like building Lego with boxing gloves. Without tools that probe such incredibly small distances, any structure on these distances is simply inaccessible. This is believed to be the case for the extra dimensions of string theory, the extra 6 spatial dimensions wrapped up very, very small. But M-theory takes this counterintuitive concept a step further. Imagine a 2-dimensional M-brain, an incredibly high-tension shrink-wrapping surface wrapped around a long, thin wire. Objects under tension want to shrink and fold up. Think of the spandex material of a morph suit. This is a 2-dimensional stretched object which is under tension and has a natural tendency to shrink its surface area, so that it tightly wraps the object which defines the boundaries, in this case, the human inside it. And so the extreme tension of the brain shrinks it down and wraps itself around the wire, effectively turning it into a 1-dimensional object. And much of the connection of M-theory to string theory relies on this idea. Brains wrapping around small dimensions, thus becoming lower dimensional objects. Objects which would, in string theory, ultimately make up at a fundamental level the world we experience. Where one of the 11 dimensions of M-theory becomes very small, much smaller than any of the other dimensions, the 1-dimensional strings of string theory would emerge from the truly fundamental 2-dimensional brains of M-theory, in part by wrapping around the small extra 11th dimension, thus becoming 1-dimensional. Indeed, all 5 string theories emerged as various limits of 11-dimensional M-theory with 1 small dimension. Our universe would hypothetically exist on one of the low-energy boundaries of this mysterious M-theory, a world of strings born from wrapping higher-dimensional brains around minuscule, extra dimensions. And so, on that California morning in 1995, a new view of string theory appeared out of the mist, one in which even the strings themselves were not fundamental objects, arising as they did from another even more fundamental object. Mathematically, this was remarkable. But what did it mean for reality? Could the brains of M-theory ever really make predictions about our world, of a hot Big Bang, an expanding universe full of majestic galaxies? When you look closely at the surface of a pond, you can sometimes see insects perched there, water boatmen or backswimmers. They skit along the surface, apparently oblivious to the depths below or the great heights above. For such insects, it appears that the water surface is their home, and they are confined to it, separate to the great bulk above. And perhaps some scientists wonder, the same is true of us. As for the insects on the surface of the pond in 3-dimensional space, so for us, living on a brain embedded within higher dimensional space. For as well as the fundamental 2-dimensional M2 brains, M-theory also predicts 5-dimensional M5 brains. When wrapped around both the small extra 11th dimension of M-theory and one of the small dimensions of string theory, some physicists have speculated that these 5-dimensional brains could become 3-dimensional, and large enough to fill a universe. And so perhaps, they say, we live on such a brain. embedded within a higher dimensional space, and the electromagnetic weak and strong forces that make up the standard model of particle physics are fluctuations which spread out along the brain, confined to its surface. As ripples are confined to the surface of a pond, so waves on a brain would be confined to the surface of this three-dimensional brain. Though were this to be true, the one exception would be gravity. Gravity, it seems, is the most universal of forces, and it follows from the equations that gravity is not, and can never be, confined to the surface of a brain. Its force lines spread out not just within, but also away from the brain. It is this that provides one possible explanation for why the gravitational force is so much weaker than all the other forces. With just your little finger and its electromagnetic nerve impulses, you can pick up a pen against the gravitational pull of the entire Earth, all 6 billion trillion tons of it acting together to pull the pen downwards. Why? What makes gravity so much weaker than the other forces? Perhaps this is because our universe resides on a brain inside a 10-dimensional space-time, and while the strong, weak and electromagnetic force lines remain within the brain, the gravitational force lines spread out in additional dimensions, thus reducing their potency. Our cosmology, only a fraction of the truth of heaven and earth. And that is not the only road physicists and philosophers have gone down when exploring the brain world. Brains and the possibility of two colliding brains also appear in cosmological scenarios for the early universe. In the idea of brain inflation, the enormous tensions and energies associated with brains would have been responsible for driving a period of enormously rapid accelerated expansion in the early universe. In this scenario, the motion of a brain through an extra-dimensional bulk would have been responsible for generating the early acceleration of the universe we believe occurred. In another scenario, called the ekpyrotic scenario, in the far past, another brain would have travelled towards our brain, colliding through and past it. The legacy of this collision would be a series of small deformations on the surface of our brain, which would subsequently grow under gravity to the cosmic superstructures, galaxies and clusters of galaxies which we observe today. And so, the possible ramifications of living on a brain are intriguing, but why imagine exotic and speculative higher dimensional cosmologies unless we have any reason to think that they could possibly be correct? That these notions of brains and M-theory actually make any sense in the first place. There is one ordeal all theoretical physicists face at some point. A thick envelope arrives containing a neatly printed book. The accompanying letter explains, "Since retirement, I have been developing a new theory of nature, and I think I have found some errors Einstein made. Perhaps you would be so kind to take a look." The manuscript will be, in Pauli's phrase, not even wrong. Instead, the concepts will be undefined, the sentences will not follow from one another as ill-defined equation follows ill-defined equation. To an expert in theoretical physics, the manuscript is clearly nonsense, even if to an outsider, one complicated equation looks very much like another complicated equation. And so this question lingers on behind every new development. Is something similar true of M-theory? Is it not even wrong? There are two notions of correctness in play here. The first is the question of whether M-theory is a true theory of our world. If we look at the universe on the deepest possible scales, if we look to smaller and smaller distances, higher and higher energies, will M-theory be the ultimate theory of our existence? Are string theory, M-theory, and brains included as part of the same great painting that features Newton's laws of gravity, Maxwell's laws of electromagnetism, the special and general theories of relativity, and the standard model of particle physics? Are they true? Theoretical physics is hard at the best of times, even when operating together with experimental evidence. And this is a problem, for the ideas of string theory and brains and other theories of quantum gravity tread an especially lonely path, a path beyond the direct reach of experiment. For there is absolutely zero direct experimental evidence for M, or string theory. Direct experimental evidence would require us, as a species, either to devise or build large experiments and large colliders which can determine the truth about this universe. And for theories of quantum gravity, this is a very hard task. To put this challenge in perspective, the Large Hadron Collider reaches energies that are smaller than those required to test the scales of quantum gravity by a factor of 100,000 billion. To build an equivalent collider that could reach energies at the quantum gravity scale using the same technology, a similar set of magnets running the entire way round the Earth's equator would be hopelessly inadequate. One would instead need a similar circular collider around the Sun, somewhere between Mercury and Venus, which is not going to happen anytime soon. But there is a second notion of correctness, still hard to achieve, but not quite as hard as a solar system spanning collider. This is the notion of mathematical correctness, of internal consistency. How do we test that our equations actually make sense? To a non-scientist trying to follow debates about the frontiers of theoretical physics, these discussions can sometimes sound like a Pokemon battle, with scientists throwing ideas at each other. Perturbative finiteness, dualities, or background independence. Who is right? Either, both, or no one? It is very hard to tell. In principle, one may think this question is easily answered by reading someone's papers. Just go and look and see if what they say makes sense. But in practice, this is not so straightforward. Understanding someone else's new ideas takes time. How can we tell apart a wrong idea from one we simply have not grasped yet? Or, alternatively, how can we tell for sure that an idea or theory is internally consistent? And so above all, in the absence of any experimental data or even the possibility of it, how can we ever prove whether brains, hidden dimensions, and M theory are right or wrong? Does M theory ultimately represent a fresh example of Pauli's brutal put-down, an untestable, not even right, not even wrong rabbit hole of elegant equations? Or is there another way? A short distance from the never-sleeping city of New York lies the quiet college town of Princeton, and at the edge of this famous campus lies the Institute for Advanced Study, secluded amongst the woods. The professors of the Institute for Advanced Study do not need to teach undergraduates or turn up to practical classes to show clumsy students how to use an oscilloscope. Instead, they are paid to think deep thoughts. Robert Oppenheimer led the institute at one time. Freeman Dyson was another faculty member. But one of the very first hires was the most famous, Albert Einstein. Although his spell there in the latter part of his career was not his most productive era, as he struggled in vain to find a unified theory of all physics. Today, one of the most preeminent thinkers there is the Argentinian physicist Juan Maldacena. Quiet and softly spoken, there are many other physicists who are brasher or louder. Few are deeper. And so it was in 1997 that Maldacena, buried in profound thought on the physics of brains, introduced a striking new idea. Whereas M theory seems to have been named with an eye for the attention it may bring, this idea had a far more humble moniker: the ADS-CFT correspondence. This correspondence is probably the most important theoretical idea to have emerged from string theory in the last 30 years, for it leads to a profound re-evaluation of what gravity means, and also what a dimension of space means. Maldacena's remarkable insight had originated from thinking about what physics would look like to a hypothetical observer moving extremely close to a brain. There were, he argued, two possible ways of thinking about this. In the first, he imagined life on the brain, looking at all the physics in terms of fluctuations of the surface of the brain. Physics, if you like, perceived by the water boatman on the surface of the pond, and how these fluctuations interacted with themselves and each other. In the second, he imagined the brain as a gravitational object within a larger space-time, with the description now all governed by the higher dimensional theory of gravity, physics viewed by a higher dimensional external observer peering down at the surface of the pond. Maldasena's key insight was that while the actual physics had to be ultimately the same, these two different observers would use very different equations to develop these same physics. The observers living on the brain would describe these physics using a non-gravitational theory, a theory analogous to those used to describe the standard model. The second observer, the person peering close to the surface of the pond, is the external one in the bulk. This observer sees the brain as a gravitational object within space-time and describes all of the physics near it using a gravitational theory, a theory which uses all of the spatial dimensions of the brain itself, but with one extra spatial dimension corresponding to the vertical direction perpendicular to the surface of the brain. Maldacena realized that as these two theories describe the same physics, they must always give identical answers. Even though the descriptions of the two different observers appeared very different, there was only one physical system, and so the results they gave must be the same. Whatever the process, for any physical quantity one could compute in this system, there would be two different ways to obtain the answer. The first using the theory of the first observer, similar to those used to describe the strong force within the standard model, while the second was a purely gravitational theory involving an extra dimension of space. Perhaps Maldacena dared to dream it was because these apparently different descriptions were actually the same theory. In the terminology of physics, the two accounts were due to one another. Any calculation you could do in one, you could also do in the other. Famously, the Rosetta Stone allowed Egyptian hieroglyphics to be deciphered through the knowledge that the information on the stone was the same in all three of the languages used. A duality is like a scientific version of the Rosetta Stone, where exactly the same information is present, except presented in different languages. Here is one quantity computed with this theory, a product of a heroic calculation to levels of accuracy that go beyond any of those achieved within the standard model of particle physics. If you were asked to write down a random fraction, you would not be writing down these. There is no way you could write down this expression by chance. This expression arose as a result of the calculation in physics as perceived by the observer living on the brain, looking at the brain as a surface under tension which fluctuates, although in this case the surface is a four-dimensional hypersurface. According to Maldasena's duality, this calculation should be precisely and totally equivalent to a calculation done in a five-dimensional gravitational theory. And this calculation has also been done, exactly the same. All the complicated structure of the first calculation, worked out in the four-dimensional theory for those living on the brain, is reproduced by the second calculation, done in a five-dimensional gravity, which views the brain as a gravitational object inside a higher dimensional space-time. But what did this all mean? To understand this, we must first understand something about one general property of quantum theories. Some theories are more quantum than others. For some descriptions of physics, classical physics works extremely well. To describe how gravity affects a ball thrown in the air, we do not need to use quantum mechanics. Although quantum effects are there, they are so utterly tiny that we can entirely neglect them. Near a black hole singularity, quantum effects may matter in gravity, but for most purposes, they are minuscule. But for other theories, the quantum nature of the system is crucial to everything. For physicists trying to understand the details of the strong force inside the standard model of particle physics, the quantum effects are always large. And this was the surprise. For a pivotal feature of Maldasena's duality was the equivalence, the sameness, between a gravitational theory in 5 dimensions and a non-gravitational theory in 4 dimensions. It was a shocking claim that initially appeared to physicists as complete nonsense. A gravity theory in 5 dimensions being the same as a non-gravitational theory in 4 dimensions, it made no sense. But this was the key. The fact that on first appearance the claim was bizarre and obviously wrong is what made its truth so profound. Ever since it was first proposed, the evidence for Maldasena's bold conjecture about the physics of brains, the ADS-CFT correspondence, has piled up. And this evidence has shown again and again that brains in string theory are mathematically and theoretically consistent, even if we still don't know whether they relate to the real world. Whatever our initial skepticism, whatever our initial surprise, it seems that at least this duality is, on a mathematical level, true. Radically different theories can, in fact, carry the same information in different languages. There was no way that this could have been chance. Clearly, manifestly there was a deeper structure, a deeper, consistent structure that explained these mathematical connections. Very different starting points, very different calculations, but ultimately the same answer. And most importantly, for our understanding of the world, this could only happen if the brains of string theory were real, consistent objects. Of course, whether M-theory is ultimately the consistent theory of our world, we do not know. Yet. But we do know enough to say that it is a consistent theory of something. Deep ideas lurk behind the symbols. Space, the final frontier. Not so in the world of physics. But will the drive to penetrate the ever more fundamental parts of physics, through atoms, through nuclei, through subatomic particles and the Standard Model, down to the mysterious realm of quantum gravity, will this lead us to the fabled final frontier? Or are the explanations endless? Do they continue to cascade onwards, further and deeper, getting smaller and more fundamental forever and ever? Perhaps not. Perhaps the zooming stops with tiny quantum mechanical strings and brains at the heart of everything. We do not, as yet, know. What we can say now, though, is that the ideas of brains, of dualities, of a map of theories linked together into an overall M-theory are mathematically consistent. And just perhaps, this foreshadows physical correctness as well. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time. The newly born universe buzzed and frothed with boundless energy. Even after the raging furnace of the first few minutes had died away, temperatures universe-wide were more than 100 million degrees. For thousands of years, this primal heat burned a cosmos of plasma, a super-hot mix of particles and radiation. Until, one day, it changed forever. That day arrived when the universe was almost 400,000 years old and had cooled to about 3,000 Kelvin. In this now comparatively tepid soup, lone electrons met lone protons and finally could stick together, forming the first atoms. But this was not all, for as each electron and proton bound together, a small amount of energy was released. A packet of energy that raced away at the cosmic speed limit, the speed of light. A particle of energy born in the formation of a hydrogen atom. A particle we call a photon. A particle of light itself. This photon was far from the first, but as the universe began transitioning from plasma into neutral gas, light could then, for the first time, stream freely through its reaches. And so, our photon's long journey began. It headed out first into the universe's dark ages, a time before the first stars burned, a time before the first galaxies formed. In the eerie darkness, gravity pulled on mass to mold the first seeds of cosmic structure. But the photon sped on and noticed nothing. Eventually, the first stars burst into life around it. Massive and bloated, these ancient suns burned themselves out in a cosmic blink of an eye, as the first supergiant black holes grew rapidly between them as they eagerly devoured mass. But the photon sped on and noticed nothing. The first galaxies began to assemble. The sky lit up with the fires of uncountable young stars across the cosmos as they began to fuse the initial hydrogen and helium atoms into heavier elements. But the photon sped on and noticed nothing. Millions steadily turned into billions of years, and as galaxies grew and matured, eventually the intense light of young stars began to settle. The photon's journey could have potentially lasted forever, into eternity, but after almost 14 billion light-years of travel, a large spiral galaxy steadily came into view. Its destiny was set. Near a small blue dot orbiting a small white star, after crossing the last few thousand light-years, the photon collided with a piece of metal, part of a telescope built by humans and orbiting near the planet Earth. The photon's energy was completely absorbed, energizing electrons and registering on detectors. But as the photon vanished from existence, its billions-year-long journey complete, it still simply did not notice. Because, to the photon itself, the journey never took place. 13.8 billion years of cosmic time disappeared in an instant. Yet how can this be? Light has existed in the universe from its earliest moments and will continue to exist long after humanity and the stars are shred to dust. But just how does it work, and how can it seemingly last forever? And perhaps most importantly, what even is it? Light is fast. It only takes 0.13 seconds for it to circulate the entire globe. Through fiber optic cables, that slows down by a third, but that still means that with Surfshark, changing your virtual location is almost instantaneous. Surfshark have been kind enough to sponsor this video, and they are the best, simplest VPN service out there. You can change your country quickly and easily to stream whatever you want from wherever you want in the world, with more than 100 countries to choose from. Light seems to escape definition as it exhibits properties of both a particle and a wave. And now you too can be similarly inscrutable to big tech companies and cybercriminals by using Surfshark to mask your IP address and encrypting your data on public Wi-Fi. It's the best way to secure your personal information when using the internet, and even warns you of potential data breaches. So check out Surfshark by clicking on the link in the description and get 83% off and 3 months for free, as well as a 30-day money-back guarantee. Thanks to Surfshark for supporting educational content on YouTube. Light had played a pivotal role since the cosmos's very beginning. In these earlier times, it had only existed for the very briefest of moments, slamming into speeding particles before it had a chance to travel anywhere, one piece of light dying as another was born. However, our parcel of light was born into a very different, very transparent universe. With the cosmic maelstrom of the Big Bang finally abated, our photon could begin its immense journey unhindered. As it traveled, many generations of stars led to our sun, and billions of years after, humans began to walk on the surface of our small, rocky planet. And so eventually, as our photon was a couple of thousand light-years distant from Earth, those humans began to wander. All men by nature desire to know. An indication of this is the delight we take in our senses, and above all others, the sense of sight. This, most of all the senses, makes us know, and brings to light many differences between things. The ancient Greeks wondered if light emanated from the eyes, touching and feeling the world around us. But clearly there are times when it is dark, when we can't see anything. So they concluded light must be something external, something captured by our eyes. Islamic scientists went on to unravel the properties of light, finding rules of reflection and the magnification properties of glass lenses. Light was clearly a natural part of the universe around us. But it took the coming of the scientific revolution and a fight between two giants of science for light's deepest secrets to be finally uncovered. The year was 1652, and Dutch physicist, astronomer, mathematician, and all-round genius Christian Huygens was exploring optical phenomena. He had noted how light travelled through lenses and bounced off mirrored surfaces, and was particularly interested in the phenomenon of refraction, where the path of light is bent when it passes from one medium to another. Huygens noticed that light was often split into the colours of the rainbow by his instruments, and sometimes strange patterns of dark and light would be produced, clear evidence to him that light was some sort of wave, some sort of travelling, oscillating phenomenon. Oscillations can be found throughout nature, from planetary orbits to vibrating electrons. But let's start with a simple picture. Think of a child on a swing. As they swing, their position oscillates from one position to the next and then back again, just like a pendulum that drives the regular ticking and tocking of a grandfather clock. When oscillations act in unison but slightly out of step, waves are formed. A stone thrown in a flat pond pulls the water down with it, but the water bounces back. This splash of water pulls on its neighbours, inducing them to oscillate, which in turn pulls on their own neighbours. These oscillations fan out across the pond as a steadily rippling pattern of waves. Waves are everywhere, from sound waves coursing in the air to ocean water waves driven by the wind and moon. Seismic shifts can generate violent and destructive earthquakes in our planetary crust, whilst similar waves ripple in the atmosphere of the sun and other stars. And so, light seemed also to be a wave. But this left an obvious question. If light is a wave, just what was doing the waving? In Britain, Robert Hooke also reached a similar conclusion about the nature of light, and he realized that this picture of wavy light could explain a lot of the phenomenon he had seen. This was cutting-edge science at the time, but Hooke had a problem, and that problem was a man. There are no surviving portraits of Robert Hooke, and over the years a rumour passed down the generations that this powerful man was to blame, having conveniently lost the painting when taking over as head of the Royal Society in London. For Robert Hooke had a powerful enemy, and that enemy's name was Isaac Newton. Since cleared of any wrongdoing in the absence of contemporary images of Hooke, there is still little question that the two men were not friends. For as well as his far-reaching discoveries in mathematics and gravity, Newton also had an interest in optics and the nature of light itself, and he did not like what Hooke or Huygens had to say. Indeed, it was Newton who discovered that white light could be split into a rainbow by passing it through a prism, and like Hooke, he had kept musing on this. But unlike Hooke, Newton did not conclude that light was some sort of wave. To Newton, light consisted of corpuscles. To Newton, light was made of tiny, individual particles. Newton's focus was the phenomenon of diffraction, the fact that waves bend around a sharp edge. He knew that sound, a wave in the air, bent as it travelled past sharp edges. It was clear that you could eavesdrop on a conversation from around a corner without being able to see the gossipers. You could hear from behind an object, but you could not see. So, he reasoned, light simply could not be a wave. And he didn't stop there. Newton went further. Much, much further. He reasoned that light, as a stream of particles, would even feel the pull of gravity. In his book Optics, published in 1704, he wrote, "Do not bodies act upon light at a distance, and by their action bend its rays?" And though on this he was correct, he was not proved correct for centuries. So it was Newton's corpuscular theory of light that reigned supreme, due more to his weight of personality and scientific standing as opposed to its ability to explain the complex observations of light. Over the years, however, steadily the tide began to turn away from Newton. In 1800, polymath Thomas Young shone light through a pair of narrow slits and observed a pattern of interference on a background screen. This wasn't the first demonstration of interference, but it was the clearest. How could Newton's picture of light as particles explain Young's observation of interference? How could light, as tiny bullets passing through either one slit or the other, produce the observed pattern? Simply throwing a couple of pebbles into a still pond reveals that interference is naturally produced by waves, either in water or in light. Other observations of light supported its wave-like nature, including light's polarization through a material called calcite. But for centuries, the big secondary question remained unanswered. If light was a wave, just what was doing the waving? Our cosmic parcel of light was born when a proton captured an electron. It sped out into the universe, powerful and energetic. But as it traveled and the universe expanded, it started to lose some of that energy. The light, originally blue to our eyes, steadily morphed through the colors of the rainbow and into the red. Soon it was joined by other energetic light shining from countless billions of newly formed stars. There were different types of light as well, light of exceptionally high energy and light with barely any energy at all. The universe was awash. Of course, our light did not know that these would be invisible to human eyes, for it would be many billions of years until eyes existed. And indeed, these X-rays and radio waves, as we call them, were unknown to us until the very end of the 19th century. In this new era, thought itself will be transmitted by radio. Guglielmo Marconi was at his father's estate near Bologna in Italy. He was still a young man, aged only 20, but his education had opened his eyes to an invisible world. In the decades before, the nature of light had steadily been unraveled, and Marconi was ready to use this newfound knowledge to change everything. Staring at his equipment, Marconi was waiting to see a faint spark in the darkness. With the bundle of wires and coils of his workshop, such a spark would not be surprising. But the impetus for this spark was not in the equipment before him. It was in similar equipment located several miles away. Of course, the 19th century had seen the arrival of the telegraph, where electronic pulses were sent along wires that crossed entire countries and continents. But this needed wires to be strung through the air and under the oceans. Marconi had no need for such wires. He would be sending messages not along bits of copper. His messages would simply fly, completely unseen, through the air. But how? The answer lies with one of science's greatest geniuses. The answer lies with James Clerk Maxwell. When a young James Clerk Maxwell arrived at the University of Cambridge in 1850, he was told that attendance at the 6 a.m. church service was compulsory for all students. The Scottish-born prodigy had long been a night owl and simply responded, I suppose I could stay up that late." His name is writ large across the modern world, but his crowning achievement was uniting two seemingly disparate phenomena and creating something remarkable. Electricity and magnetism had been known about since ancient times, seen in the strange attraction of rubbed materials and mysterious stones that knew how to find north. But by the 19th century, it was becoming clear that these two were not truly distinct. A flow of an electric current could generate a magnetic field, and a changing magnetic field could generate a current in a wire. But as Maxwell stared at these equations, he began to see a deeper picture. instead of separate relationships, he saw that electricity and magnetism could be united into a single whole, a united set of mathematics that encompassed all electric and all magnetic phenomena. But Maxwell's great insight was not only concerned with electromagnetic complexity, for he wondered about the simplest situation of all: electromagnetism in the nothingness of a vacuum. How does light travel through the emptiness of space? Maxwell knew that electromagnetic fields filled all of space, even in vacuums, but it was imagined that in empty space these fields would be null, effectively not there. But what if you plucked one of these fields, either electric or magnetic, so that these fields were not at zero at some location? Maxwell pondered this question, using his equations to explore how the situation would evolve. And the answer was astounding. Think about pinching the skin on the back of your hand. What happens when you let go of your pinch? Your skin sinks back to its unpinched self, quickly if you are young and somewhat slower if you are older. Maxwell's equations told him that the electromagnetic pinch would evolve away back to zero, but that this was not the end of the story. Pinching the electric field would generate a similar pinch in the magnetic field, and the pinch in the magnetic field would generate a pinch in the electric field. And these pinches did not simply fade back to zero. Instead, they oscillated, regenerating each other from one moment to the next. And just like ripples on a pond, these oscillations traveled away as waves. And so Maxwell realized these oscillations had the property of light. Light, he realized, is a self-propagating electromagnetic wave. But what was causing the ripples? What was the electromagnetic equivalent of the stone thrown in the pond? He saw that it was electric charges, something we now know as electrons. As these charges jiggle and oscillate, they disturb nearby electric and magnetic fields, and these disturbances ripple away as electromagnetic radiation, what we call light. He also realized that the inverse must be true, as light entered the eye and fell on the retina. The oscillations of the light must cause electrons in atoms in the eye to jiggle, and it is this jiggling of electrons in the eye sent as signals to the brain that we perceive as vision. Finally, Maxwell understood what it was that was waving, and what caused the waves. And one more thing. He knew that light had waves with a length of about 1/1,000,000th of a meter, but his equations showed no limitation on the wavelength of his electromagnetic waves. And so he concluded that there must be light with both long and short wavelengths that is invisible to the eye. It would take 2 more decades for the answer to this puzzle to present itself, decades in which Maxwell died of cancer at the age of only 48. In 1886, Heinrich Hertz, working at the University of Karlsruhe, was the first to find these invisible waves. Named Hertzian waves after their discoverer, a new revolution had been born. We now refer to these Hertzian waves as radio. Hertz was understandably very pleased with this discovery, but when asked about the practical use these radio waves have, he apparently responded, "Nothing, I guess." And yet, it was these radio waves that only a few years later Marconi was using to send messages across miles, and then across counties, oceans, and all across the immensity of the globe. In 1909, Marconi received the Nobel Prize for his work on wireless telegraphy. Hertz, however, died in 1894 at the youthful age of 36, never seeing the true promise of his discovery. The world was set to become full of invisible light as the 20th century began, and the mystery of light's properties seemed settled. That was until 1905, and a remarkable year for one German patent clerk. The universe continued to change and evolve as our particle of light traveled. The mixture of light joining it on its journey reflected that change, bursts of radio waves and high-energy gamma rays becoming more and more frequent. This energy surged through space, much of it flowing between the stars and into the darkness. But some encountered lone atoms in the emptiness of the void. The low-energy radio waves very gently shook and energized these atoms, like a calm ocean wave lapping at a sandy shore, just as we would expect from Maxwell's picture of electromagnetic waves. But the behavior of the high-energy gamma rays was different. They delivered their energy to the atoms with a violent punch that ripped electrons clean away, not a lapping ripple, but an isolated smash. The gamma rays hit the atoms not like waves, but like hard, little, energetic particles. But how? Could Maxwell be wrong? Could, on some occasions, light be more like Newton's vision and act like a particle? And if so, just what would those occasions be? For the present, we have to work on both theories. On Mondays, Wednesdays and Fridays, we use the wave theory. On Tuesdays, Thursdays and Saturdays, we think in streams of flying energy quanta, or corpuscles. Alfred Nobel had made his fortune through his inventions and his businesses, especially in the field of explosives and weapons. And so, perhaps not unfairly, in an 1888 obituary in a French newspaper, he was called the Merchant of Death. This surprised Nobel, firstly as he was still very much alive, but secondly, and more distressingly, because he realized what his historical legacy was to be. So, in his will, he decided to leave most of his fortune to a series of prizes that would honor those that have conferred the greatest benefit to humankind. Across science, the Nobel Prizes are perhaps the most prestigious, the list of winners replete with the giants of science over more than a century. And in 1901, the inaugural Nobel Prize in Physics was awarded to the German Wilhelm Röntgen for his discoveries about the nature of light. For it was he who discovered the X-ray. Röntgen's experiments with various materials found that only the densest could halt X-rays. He even managed to convince his wife, Bertha, to place her hand in the beam, after realizing his X-rays should stream through her flesh, but be partly blocked by her denser bones, thus producing the first X-ray photograph. Whilst it was suspected that X-rays were electromagnetic radiation with a wavelength much smaller than visible light, as opposed to radar, which was much longer, it took several decades to conclusively show that this was the case, although in the meantime the medical application of X-rays to fix bones and save lives grew without bounds. And so this meant that by the early 1900s, Maxwell's vision of electromagnetic waves beyond the visible had been undoubtedly confirmed, all of light's secrets uncovered, even the electron having been discovered. All that remained was to find the rest of the light we could not see, gamma rays, microwaves and more, to fill out the last gaps on the electromagnetic spectrum and wrap up the story. But of course, if physics feels that a job is done, a rude shock is usually just around the corner. In Maxwell's picture of light, it could be thought of as a continuous wave. Scientists had found that when light crashed into most materials, it continuously dumped energy that energized electrons, causing them to be emitted. This was called the photoelectric effect. By lowering the intensity of light, it took longer for energy